So the only thing that wasn't very elegant in the algorithm that we came up with in the last unit that inverted the matrix was that it required two sweeps through the matrices. The first sweep applied all of these Gauss transforms and did most of the work, and then we had this second sweep where we had to go and divide by the diagonal elements in order to make matrix A into an identity matrix, and the matrix B, that was the right-hand side matrix, then saw all of its rows scaled. So what we're going to do now is a small modification to our approach and our algorithm that allows us to sweep through the matrices just once. And the idea here is as follows. Okay. What we have here is something that looks suspiciously like a Gauss transform, but notice that now we also have a -1 on this diagonal. Now what does that -1 on the diagonal do? If you look at it, if you view this as rows, you end up doing -1 times the first row and then 0 times the second row and the third row. So that means that the first row is merely multiplied by -1. And notice that that is done in an effort to put that 1 that should be there eventually, because we want to make it into an identity matrix, there from the start. So that now happens as part of our Gauss transform application. If you look at that and you look at the computation, you then end up with this matrix on the right here. And then here we did exactly the same thing. We still computed the same multipliers as before, which means we're still taking the same multiple of the current second row and adding that and add that to the last row. But now we also introduce a diagonal element that has the net effect of making the diagonal element here into 1. And when we march through that, eventually what we end up with is an identity matrix right here, and then the inverse matrix right there, which you can verify by multiplying out the original matrix times this matrix that has just been computed. So notice that we just swept through the matrices once. We didn't have to do the second sweep where we applied the diagonal, the inverse of the diagonal matrix that A had become. So what's going on here? Well, now we have a Gauss transform that is slightly different in that it has some diagonal element there. If you multiply that, you notice that this right here multiplies the current row. So therefore you can choose that so that this here becomes 1. You still end up doing exactly the same computations everywhere else. So you can still compute your L21 and you use 0, 1 in an effort to put zeros right here. And then you still have the same rank 1 updates happening everywhere else. So the only difference really is that this row now is also scaled. Which leaves us then with this right here. So if we had an identity computed so far already, what we now do is we introduced another column that becomes part of the identity that is being computed on the left side, and that then gives us another column on the right towards the inverse. The algorithm, you're going to have to look in the notes carefully because there are a lot of details here, but this here explains how all the different parts of the matrix are actually updated. And what this gives us now is an alternative to the Gauss-Jordan algorithm that computes A inverse in one sweep. Now, there is a challenge question in this unit that asks you to actually modify this algorithm so that it overrides the original matrix A, so you don't have to start with a matrix B that has been set to the identity. And what we hope you'll do is actually think that through and then try with the IPython notebook to actually see if you can come up with the right algorithm.